So which is something like this: m d2x dt square plus c dx by dt plus kx equals to 0. And we have been given the initial condition that the displacement at time 0 equals to 1. Yeah, hello.
Hello, Suman.
Yeah.
One second. Sorry for the interruption. Prayag,
Yes.
have you started that live?
Yeah, I
Yeah,
have.
I think yes.
I
I'm
just
sorry.
started. Yeah.
Okay.
So I mean, like, should I start once again, or I mean, was it captured like the first few
You
minutes?
can continue.
Okay, thank you. So what we can do is that we can, how to solve this thing is that in MATLAB, we have to convert this second order ODE into two first order ODEs. So what we can do is that we can take dx by dt equals to v, like here we have done. And because we have the initial condition that the displacement at time 0 equals to 1, so we have our first order equation. It's one of the first order equation, that is dx by dt equals to v, and the initial condition is x of 0 equals to 1. So in our problem, we'll be looking at the initial velocity as 0.25. So if we put dx by dt equals to v here, then it will be something like this: m dv by dt, because d2x by dt2 will be dv by dt plus cv plus kx equals to 0. So this is our second first order equation. And if you remember that Venudar did a session on how to solve ODEs using Euler method and a MATLAB function called ODE45. So once again, we'll be looking into it, how to solve them. So we have converted our second order ODEs into two first order ODEs. Now, let's say we have been given the initial condition as y equals to x and v, where x is the initial displacement, I mean the x denotes the displacement and v denotes the velocity. So what we can write is that dy by dt equals to, because dx by dt equals to v, so it's equals to v. And if we do some algebraic manipulation, then we get dv by dt as minus of cv plus kx whole by m. So we'll be just trying to we'll be trying to solve this using two cases. One is c equals to 0.5, which is an underdamped case, and c equals to 5, which is an overdamped case. And we'll keep the mass to 4 kg and k, the spin constant, as 2 Newton per meter. And as I have said, that the initial displacement is 0 at time 0 equals to 1, and the initial velocity is 0.25. Okay. So Venudar had already given you a session on OD45, but still let us look at the syntax of it. So firstly, we have to give this t sol comma y sol. We can give any name as you wish. So what it gives is that it gives, this is the time variable, the time vector, and this is the solution vector. And this is that f name. We have to provide the function which depicts, which returns the function. I mean, like the original equation, because see, I mean, like we write a equation like dx by dt equals to v. That means the function is v here. So we have to provide v, and respectively for the second one, we have to provide this thing, that is minus cv plus kx by m. And this is, what is this? This is t, no, what is this? This is t naught and t end. Yes. So this is the final, I mean, the range of the timing we want, I mean, for the solutions we want, t0 comma tn, I mean the range between which we want the solution. So let's say we will do our solution from 0 to 20 seconds. So my t0 will be 0 and t end will be 20. And I can give some spacing as I desire, that depends upon the problem. And y0 is the initial conditions. So our initial conditions will be, because y0, I mean, look, we have initialized y as x and v. So y0 will be x0 and v0, and x0 is 1 and v0 is 0.25. So our y0 will be a vector of two elements. One will be, the first element will be 1, and the second element will be 0.25. Okay, so now let's try and code this. Let's give it the name conversion of second order ODE. Okay, now we'll be giving the parameters. So our mass was given as 4 kg. Spin constant was 2 Newton per meter. And let's first do for the underdamped case, where the value was 0.5. The damping coefficient was 0.5. Now the initial conditions for y, because our initial displacement was 1 and the velocity, initial velocity was 0.25. So we insert this. Now we will give the uh, time span for which we want to calculate the OD of the function. So let's, as you said, that we will start from 0 and we'll go to 20. So let's give a spacing of 0.2 between them. You can choose the spacing as your choice and also upon the question given at certain times. Now we'll be creating the function because we need the function while we'll be using the MATLAB inbuilt function ODE45. So we have to create a function from beforehand that expresses our two ODEs. Okay, now one thing about ODEs is that, like, let's say at time t0, you have a certain value. And using that value at t0, we calculate the value at t1. So we will be needing two independent variables, that is t, comma y. Means that is time and the function. Oh, it will be small y. So I am taking y means I am taking this is a vector actually, this y here, and this has two elements. The first element denotes the displacement, and the second element denotes the velocity. So our first OD was this thing, that is v, and because this is the second element of y, so I will write y of 2. Now the next will be this equation, that is minus cv plus kx by m. And once again, because v is the of 2 instead of v, and for x we will use y of 1. And because c is already a constant, so we will not be using the dot multiplication, do with the simple multiplication and divided by the mass. So we have initialized our function. Now we will be solving the equation. Okay. So the t solve will give us the values of time, and the y solve will give the value of the function, I mean the ODE in those respective times. So we'll be using ODE 45, the function name f, and then the span of the time period within which we want to calculate the ODE of the function. So because we have already initialized it as t span, so we can give t span here. And the initial condition for y also has been given as a y0. So we'll give y0. So this should give us the solution. Let's run this once. Okay. So let's see this. So t-sol is basically the time interval from 0 to 20. So see 0, 0 0.2, 0 0.4, 0 0.6, 0 0.8, and so on like that. Now let's look at y-sol. So y-sol, what is this? That the first column indicates the displacement, and the second column, all rows of the second column displacement indicates the velocity. So all the elements in the first column will indicate the displacement, and all the elements in the second column of y-sol will indicate the velocity. So now let's make a plot. First, let's do it for displacement. Now one thing we will do here, we will try to do two plots in the same page. Like the above one will have displacement, and just below that we'll try to plot the velocity. So what we have to use is that we have to use subplot here, because I want two plots. So I'll write 2, 1, and because this is my first plot, so comma 1. Now I will plot t sol comma y sol of, because my first column of y sol, I mean all the elements of the first column of y sol was my displacement. So for all the elements means a colon will indicate that all the rows of y sol, comma 1 will indicate the column number of y sol. So this will help me plot the displacement with respect to time. Now let us also give some x labels. So the X label will be time and the Y label will be displacement. Okay, let's copy this and we will just make a few changes for velocity. And because this will be my second plot, so I'll have to change here 2 here, and I need the velocity to plot. So I'll have to change from column 1 to 2. The X label is fine, it's still time, but this will be velocity. Okay, so we're good to so far. Let's run this. So this is what you see. There are oscillations. So we can say that this is an underdamped case. This is the displacement time graph, and this is the velocity time graph. So let us look at this for a overdamped case. Let's see whether it gives the same graph that we know. Yes, it actually does this should be the graph for an overdamped case. There should be no oscillations. It should go straight to the point here. So this is it. And this is how you convert a second order ODE into a first order ODE. Okay. So now we'll be looking into a.
Excuse me, sir.
Yeah.
Sir, the previous code, what is Y1 and Y2, sir?
Which one?
Line number 11. Line number
The Y1
11.
and Y2. Okay. Okay, let's go back to the slides once again. Look, what I'm trying to do is that I'm trying to create a matrix Y, which has the has a displacement and velocity within it. Okay. I want to calculate displacement and velocity. So what I'm doing is I'm actually creating a matrix which has these two things. So my Y of 1 is the displacement X, and my Y of 2 is the velocity V. And my dy by dt, that is the function, the ODE function is, the first ODE is V. So that is nothing but Y of 2, because I have initialized that Y of 2 as V. The function argument I have given here Y. So it is a vector matrix Y which has displacement in its first element and the velocity in its second element. So the Y of 2 is the velocity here. And this denotes my first order, the first ODE. And this is my second ODE. And my second ODE goes like this: minus of C into V plus K into X. And because V is Y of 2 here, so it will be minus C into Y of 2 plus K into Y of 1, that is X. So are you clear with this?
Yes, sir. Yes, sir.
Okay. So let's move ahead.
Sir, similarly, that Y solution will be like a matrix. So Y1 will be displacement and 2 will be velocity.
Yeah. See this. The first column is the displacement.
Okay.
Starting from 1, and it's going as it should be. Whatever the MATLAB function has solved, it's giving that. And the second column is giving me the velocity.
Okay. Thanks.
Okay. So now we'll move on to the next mathematical model. That is the predator-prey model. This is very simple and very common also. Many times the applications of OD classes start with this example. So what this says is that the Lotka-Volterra model is one of the first and simplest form of model that captures the dynamics between a predator and a prey. So if H is the normalized population of herbivore prey and P is the normalized population of the predator, then the model equations are given by this form. So my dH by dt equals to alpha of H minus beta H into P. And note that H and P are the respective normalized populations. The H is for the prey and the capital P is for the predator. So once again, we have two ordinary differential equations, but they are in first order only. And the parameters are also given here. Alpha equals to 1, beta equals to 0.25, gamma equals to 0.25, and delta equals to 2. And the initial values has also been given to us. That is H of 0 is 1 and P of 0 is 1. But instead of using ODE 45, we have another MATLAB function, ODE 15s. It is also used for solving ODEs. But the ODE 45 actually uses adaptive Archifold method. it uses some other method. I'm not quite sure right now, but this is said to be more efficient than the ODE45. And we will be solving this from for the time span of from 0 to 15 and with the interval of 0.2. And then we will try to plot the results. So let's go ahead. Okay. So let me clear this. Now what name should I give this? Okay, let me give editor, predator, prey. So we'll firstly provide the constant that has been given to us. So alpha is 1, beta and gamma is 0.25, and the delta is 2. So alpha was 1, beta and gamma was 0.25. And delta was 0.2. Sorry, just 2. Now let us give the parameters that also was given. Like the t span, that is the time span, was given from 0 to 15 with an interval of 0.2. And my initial conditions were, both were 10. Like this is the initial condition here. Oh, sorry, it's 1 here. Then it will be better for using 10 actually. I mean, 1 is too small a number for population. So let's do it for 10. Now we have to create the function. Now once again, we'll be using the same methodology that we used earlier. Because I have given my initial condition as y0, and it is the first element is taking the normalized population of the prey, and the second element is taking the normalized population of the predator. So once again, we will be using something like that. Obviously, we'll start with an at the rate symbol. And because the OD, as I said earlier, that OD requires the earlier functional value at the time stage. I mean, like for getting my value at t equals to 0.2, I need my value at t is 0. So I also have to give this expression t as a variable and y. And once again, my y is over here is a matrix which has 2 elements. The first element denotes the prey, and the second element denotes the predator. Now let's go back and see the equation. So we will give the first equation, that is for the predator, the prey equation. We'll give it first. So that is alpha into h minus beta into h into p. And let me say you once again that h is my first element of y and p is my second element of y. So my first equation will be alpha multiplied by h, that is y of 1, minus beta multiplied by y of 1, that is h, multiplied by p, that is y of 2. Now the next equation. What's the next equation? The next equation is gamma into h into p minus delta p. So gamma multiplied by h, that is y of 1, multiplied by y of 2, that is p, minus delta p. Okay, so we have done with the creating the function. Now let us solve this. Okay, well, I forgot to say about ODE15s, that the syntax is the same as the ODE45. We have to provide the function name, the time span for which we want to calculate the ODE, and the initial values. So the syntax is same, just we have to use ODE15s instead of ODE45.
Excuse me, sir.
Yes, hello.
Sir, can't we do can't we give function as like t comma h comma p?
What?
So
What is it?
in line number 14,
Mm-hmm.
Instead of giving t comma y,
Mm-hmm.
can we give t comma h comma p and use alpha into h minus beta into h into p, something like that?
Yeah,
Can we
that
use?
also can be done. But
Okay.
what this does is, because I mean it's easier to, I mean, like, what to say, provide actually,
Okay. Okay.
because you'll
Hello.
be getting, yeah, hello. I mean, if
Uh,
you want to do like that, what you have to do is that, actually you cannot, then you have to create two functions then, not one function. What am I correct?
Like
am I
how
are you
sir?
getting what,
Like
I mean, why you have to create two functions is that, because, I mean, like, in the initial guess, you have to provide only one initial guess, right? So then either you have to give it
yes
for
sir.
h, either you have to give it for p. So you have to create two functions. So you give a function name, you give the time span, and then you give the what is that called? What is the, I mean, the initial guess for h or p.
Then we will have to solve two equations usually.
Yeah. But let me try it once. I think yours also should work actually. Okay, let us solve this first. I
Okay.
mean, the way I know, and then we'll try it your
Okay.
way as well.
Okay.
I think this
Hello.
should work. Yeah,
Uh,
hello.
Hello, sir. Can you repeat how to create the function? Actually, I joined a little bit later, and so I actually missed that part. Can you repeat that?
Okay. Yeah, sure. So, these are the two ordinary differential equations we want to solve, and they are actually interrelated. This is a predator-prey model. Okay. So as you can see that the dependent variables in both of them have h and p. So they're dependent on each other. Okay. So this is my first ODE and this is my second ODE. So if I wish to create this function, so what I have taken is that I have given two independent variables in the function. Firstly, the time. Whenever we are working with the ODE, we have to give time. Okay, because I mean, like, when solving ODE, whatever the numerical method, it actually uses the earlier time value to calculate the next time value. So we always have to provide t whether or not our function has the value t. And the second argument what I have used is y, and I am stating that this y over here is a matrix, and it has two elements. And the first element is my capital H, which is the normalized population of the herbivore, and my second element of y is the capital P, which is the normalized population of predator. So when I am creating this equation, so my equation goes something like that: alpha into h minus beta into h into p. So I have written alpha into y of 1 because I am stating that my y is a 2 cross 1 matrix where the first element is the h and the second element is the p. And similarly, this equation also follows this expression, and the y of 1 over here is again h and y of 2 is p. So are you okay with this now?
What the @ symbol does? What is the function of this?
I mean, @ symbol indicates that I mean, these are the independent variables for the function. Are you getting my point? Like, whenever, like, a function of x, like if you say sine of x, that means x is the independent variable, right? Similarly, in this function I'm creating, t and y are my independent variables.
Okay. I mean here in the first part, I have to put the variables and then I have to write down the functional form.
Yeah, the functional expression. This is my
Okay.
@ t comma y, means that these are the variables with
Okay.
which I'm using the functional expression, and then this is my expression. This was my expression through this equation,
Okay.
and this was my
And
second equation.
here we have created a 10 question matrix in y, and then
How many? What you're saying? Why? How many metrics?
y is a 2-column matrix, obviously.
Yeah, 2-column matrix. Yeah.
2-column matrix, and then we have created y0 as is this the initial condition? 10
Yeah,
10
y0 is the initial condition. Yes. This is actually
because,
not
because
2-column
we have to
matrix. This is,
use the initial values of y in the later part.
yeah.
Okay.
Because
And
whatever the ODE, you need the initial condition, right, for solving it.
okay.
I mean, every
And
ODE expression has to have a initial condition so that we can get further results.
here do we need to dimensionalize the y?
I'm not getting what you're saying. Dimensionalize. I mean, what do you mean by that?
Actually, what I want to say that do we need to dimensionalize y? or is it arbitrary?
Acha,
I mean,
like
should we
the
fix
first,
should we fix the dimension at first point?
I mean, that is also dependent upon you. Okay. Like for instance, I am taking y of 1 as h. You can take y of 2 as h. That is upon your choice. Okay. Are you getting my point?
No. I'm saying that do we need to dimensionalize? I mean, the number of columns. Suppose the number of the number of row. Do we need to fix it, or is it taken into the process that until I reach the p and then the steps will be followed? The
Still, I'm still not getting your point. I mean, like for the t you are asking or for the y you are asking? Like,
I'm asking why.
acha,
Actually,
acha.
in a matrix, what we have a certain number of rows and certain number of columns,
Acha, you're talking about that. Okay.
and
Okay.
here we have two columns, and I am asking that do
Not
we
two
need to
columns.
fix the
This is
rows?
actually
Do we?
2 rows actually. Hello. This is 2 rows. This is a 2 cross 1 matrix. Sorry, 2
Okay,
cross 1 matrix. Yeah.
2 cross 1 matrix. Acha.
Because
That,
the semicolon, when we are initializing a matrix, the semicolon indicates we are going to the next row.
hmm. Okay. That means the first row indicates y1, the prey,
Yeah.
and
You're
the
getting it.
second row the predator.
Yes. And you can wish
Okay.
to change it as well. Okay. I mean, because I'm taking it this way, so I have given it y1. I mean, if you want to take the value of predator first, you can do it that way as well. But you have to keep these things fixed. Like if you are taking y of 1 as predator, then you
Hmm.
also have to use y of 1 here as, I mean, this one, then this will change. Okay. Then this will
Okay.
become y of 2,
Okay. Then
because this
then
y of,
there is no point about fixing the column. I mean the number of column that we will use. There is no point about it.
no, I mean, like you have 2 initial conditions, right? There are not more than 2 initial conditions. So that is fixed already. What I am saying is that you can change the positional values in MATLAB. Like,
And
let's say if
I got
it
that
was
point.
10
I
and
got that
20. Let's
point.
say it was 10 and 20. Okay. Now are you getting my point? Let's say it was 10 and 20.
Mm-hmm.
I mean, the default value for the prey was 10, and for the predator it was 20.
Okay.
So now,
Actually, I can't clarify my question. Actually, what happens in numerical that there are certain number of steps followed. I mean, it's not like integration, simple integration, and there
mhm.
it happens in a discretized way, and so certain number of steps followed, and so what happens that in the next step the value that we calculate, that value is used from the previous step, and
Yeah, exactly.
the current value will be used for the next step, and that's why
Yeah.
we progress, and the values got stored in the matrix. And so what my point was that do we need to fix the column? I mean, that what we usually do that when we use a matrix, and we in general first we fix the dimension. Let's take that the matrix's dimension 10 cross 10, but we don't need 10 cross 10 elements. Suppose we need 5, but we initially fix the dimension 10 cross 10. We may not use the all dimension, I mean all the slots that the matrix have.
Mhm.
So my question is, do we need to here the dimensionalize the column
Yeah,
number?
you have to fix it. Like you have to make it a 2 cross 1 matrix for the y.
Okay. Okay.
Okay. So now moving on.
Okay.
So I was going to solve using ODE 15s. So this is my MATLAB function, and my function has already been created. And now I'll provide the time span and my initial values. And now let us plot this. Okay, before that, let me show you the values that we are getting for tsol and ysol. So once again, you see that ysol has 2 columns here. The first column matrix is giving me for the predator, sorry, the prey, and the second column is giving me for the predator. So let's solve this. Sorry, let's plot this. So we're getting something like this, but we are uncertain that which one is which. So let's make a legend. Okay, so the blue line is indicating the normalized population for prey, and the red line is indicating the normalized population for a predator. Okay. Okay, so one of you had said that if I use H and P, let's do that. Actually, I'm also not certain whether this works or not, but I think this should work because my y0 is there, my t-spine is there, and my function has the same things. So I think this should also work. Okay, no, it does not work. Okay, then for that, I think you have to use, you have to create two functions, and then you have to get the solution for each, like firstly for the predator, sorry, for the prey, and then the predator using this, you want to use H and P.
Okay, sir. Thank you.
Okay, so this is working fine. So this is the final code. Okay, so today the session was only this much, the short session.
Hello.
Yeah. Hi.
Hello.
Yeah. Hello.
I think like when you are using H and P,
Yeah.
nowhere in the code you didn't mention about H and P. That's why I think didn't work. You mentioned why not. So it will work
Why
for
not
Y1 and
initial,
Y2.
why not is my initial conditions?
Yeah, initial condition. But you are running with H and P, not Y1 and Y2.
But H and P is
So
my,
you
I mean,
should
like
give
functions.
H as initials, right? H is equals to 10 and P is equals to 10. Then
Okay.
try it. Like I think it will work if you
I
try
mean, it's
like
the same thing. Like if I am using 10, because I have to provide the initial condition as this only. A matrix as 10 and 10. Are you getting my point?
Okay. Yeah.
So I don't think that that will make any more.
Okay,
let's
here
see.
in OD15, like we don't have any option. Like we have to write why not only.
No, not why
Initial
not. I mean, like
conditions. Initial conditions.
the
only.
initial guess. Actually, I'm not initial condition.
Yes.
The initial guess.
Initial
Like
guess.
whatever the, I mean, like function we have in MATLAB, which directly gives the result for a ODE, we have to give y0, and y0 is the initial conditions representing the y of t of z.
Okay. Thanks.
So I don't think that this will make a change, but you can try it yourself, and always Google it as well. I mean, Google is the best way to learn these things.
Okay.
When you are stuck.
Thanks.
Okay. Okay. So any more questions? Does anyone have any more questions? Okay, so I think I should stop this session now. Thank you, everyone.
Thank you, sir.
Yep.
Thank you.
So hi there, Radhika, are you still there? Hello.
Hello. Hello, Suman.
He left.
He
madam.
left.
Okay. So shall we end the session?
Yeah, if possible, the code can be shared somewhere. Slack.
Okay, sure. Thank you.